Hello, all of you. Welcome to the 37th lecture on the course on analysis and modeling in chemical engineering. In this week, we started talking about graph theory. In the last lecture, we discussed some basic definitions which pertains to the graph theory, and we ended up on like acyclic graphs, reachability matrix, and things of that sort, right? So I want to now extend the idea, whatever we have discussed, to a cyclic graph. Basically, what I said is r to the power n gives me the information regarding n step paths, and then that eventually vanishes for a acyclic matrix. The higher powers of n starts to vanish beyond a certain value of capital N that we discussed. Now I want to see like what will happen for a cyclic graph, right? And I mean, even if I do not tell you what will happen, you can always guess what is going to happen. In this case, we are going to start forming loops, right? And there are going to be endless number of paths because you can keep on going back and forth in the loop, right? Let's say, for example, from 1 here, I can go to 2, then to 3, then to 1, again go to 2, 2 to 3, then to 1. So I can keep on doing this kind of a loop. And the same is true starting from any vertex in the graph, right? That information should be conveyed in my r to the power n, what I am getting, and then we will see like what the reachability matrix therefore is and what kind of loops are present and things of that sort. So let me quickly write the Boolean matrix for this graph. As I was saying, I can label it. The rows corresponds to columns, so I am doing a label. This is not part of the graph, but this really helps us write the Boolean matrix. So from 1, there is a one step path to 2. So I put a 1 here. And from 2, there is a one step path to 3. And from 3, there is a one step path to 1. This is my R matrix. And R square is therefore R into R, 0, 1, 0, 0, 0, 1, 1, 0, 0, the same matrix. Now I will do matrix multiplication as usual. So let us say for the first row in the new matrix, I am going to see whether the second element is 1 here. So now I look along the columns of this, and whichever column gives me a second element equal to 1, that corresponding column is going to be 1. Every other column is going to be 0. So if I multiply the first row with first column, we will get 0 because second element is 1 here and third element is 1 along the column. That does not work. The same is true for the second column, but for third column the second element is 1 both for the first row and the third column. So I am going to put a 1 here, and the same idea I apply now for the second row. For the second row, the third element is 1. Along the columns, the third element is 1 for the first column. So I am going to put 1, 0, 0. And then for the third row, the first element is 1 and the first element is 1 for the second column. So I am going to have, right? And we can see what do they represent. Again, I can put a label if I wish, 1, 2, 3, 1, 2, 3. So I have a two-step path from 1 to 3. We indeed have. We can go from 1, then to 2, then to 3. So this is a two-step path. And then from 2, there is a two-step path to 1. How can we do that? We can do 2 to 3, then to 1, basically moving in the loop. And then from 3, I can go to 2 in 2 steps. I can go from 3 to 1 and then to 2. These are also my two-step paths, right? So R square, as we had earlier, represents the two-step paths in the graph. I can go ahead and compute R cube, and R cube is going to be R square into R, and again I do the row column multiplication as usual. So for the first row, third element has to be equal to 1. That is true for the first column. So I put a 1 here. For the second row, the first element has to be 1. That is true for the second column. And for the third row, second element has to be 1. That is true for the third column here. So this gives me my new matrix. And that gives me 3 step paths. Basically to the same vertex, 1 to 1, we can go as 1 to 2, then to 3, then to 1. And similarly, I can do 2 to 2 as 2 to 3, 3 to 1, and 3 to 1 to 2 in 3 steps. So basically, I can revisit the same vertex in 3 steps. Why? Because basically we have a loop forming in the 3 vertices. So basically in 3 steps, we can go ahead and do that. What if I compute R4? What do we expect will happen in this case, right? So R4, let us compute for ourselves. So R4 in this case is R cube into R. R cube gave me something like this. And R for our case is, as we have discussed, so let us do this multiplication again. So same idea. For the first row, first element is 1. That is true for the second column. For the second row, second element is 1. That is true for the third column. And for the third row, third element is 1. That is true for the first column. And I basically recover the same Boolean matrix R, right? So 4 step paths are same as 1 step path, and that's not very difficult to see because I am visiting the same vertex in 3 steps, and then I can complete the loop, come to the same vertex, and then do a 1 step path, right? So basically all the 1 step path can also be done in 4 step, because 3 steps is pretty much returning me to the same point where I began with, right? Similarly, I can say that R5 is going to be R square, and now I can extend this idea. This is also going to be equal to R8, R11. This is also be equal to R7, R10. Essentially, we can go to the same loop twice, thrice, as many times, and this will keep on going, right? So there are two things here. One, that there is a repetition with some like alternate powers of R. In this case, after 3 powers of R, there is an alteration because we have a loop formed by the 3 vertices, which is also called a cyclical net of order 3. So we have formed a cyclical net of order 3. So there is a repetition after 3 powers, right? And the second point is that now R to the power n is not vanishing, because let's say even if you have 100 power, then also I can go to the same loop, let's say 33 times, and then do a 1 step path, right? So the R to the power n is no longer vanishing, right? In fact, this is kind of a unique case where we have a cyclical net, and that itself is the graph. But what may also happen is the cyclical net is part of the graph. The graph itself may contain other things, right? But cyclical net can be part of the graph. But in this case, when I look at the cyclical net itself, then what we observe that R no longer vanishes, and there is a clear repetition in the R, some alternate powers. In this case, the order is 3, so every 3 powers later, we are having that repetition, right? Okay. So what is going to be the reachability matrix for this case? You can see for yourself. So R star is going to be R plus R square plus R cube, and maybe we can stop here because R to the power 4 is same as R, And as we have seen, if I add the same matrix to itself, the Boolean math gives me the same matrix. R plus R is equal to R. So R to the power 4 is equal to R. So therefore, there is no point adding it. R to the power 5 is equal to R square. So no point adding it, and so on. And that is going to be, so my R is this. My R square is something like this. We can see we have computed R square earlier, and then my R cubed contains diagonal terms, and now you see, if I add all of this, what we essentially get is a matrix containing all the ones. What this means is that I can reach any vertex from any vertex if I do not care about the number of steps it takes, right? So pretty much we have a loop forming. So from 1 I can go to 2 to 2 and 3, from 2 I can go to 3 and 1, and from 3 I can go to 1 and 2. In fact, I can also visit the same vertex 1 to 1, 2 to 2, and 3 to 3, right? So therefore, this R star contains all ones in the matrix. Okay. In that particular example, we had only that cyclical net forming the graph, but then you can have cases where the cyclical net is part of the graph. Let's say here in this graph, 2 to 3, this forms a cyclical net, but then there are other vertices 1 and 4 which are not a cyclical net. So I cannot revisit 1 starting from 1, and the same is true for 4, but 2 and 3 I can basically loop between 2 to 3. It is forming a cyclical net, and this is of order 2. So for these kind of cases, we have a relation that if I take an intersection of R star with its transpose, this will give me information regarding the loops, and we will see how it gives information regarding loops. So when I say this intersection of two matrices, basically we are doing a term by term multiplication of the matrices, right? So in this case, you can see, of course, I can compute R star in the traditional way, R plus R square plus R cube and so on, but let me simply make it by inspection. So R star gives me whether I can reach from one vertex to the other or not, right? So let's say 1 to 1. Can I go there? No, I can go from 1 to only 2. I cannot come back. So 1 to 1 is going to be, I can again label wherever I am in doubt, I can label it, which is not part of the matrix. So I cannot go from 1 to 1, so I put a 0. 1 to 2 I can go, 1 to 3 I can go in 2 steps, and 1 to 4 also I can go via 2 and 3. From 2 I can of course, I cannot go to 1, but I can of course go to 2, I can go to 3 and come back, I can go to 3 and I can go to 4 as well. From 3 I cannot go to 1, but I can of course go to 2 and I can go to 3 and to 4, and from 4 I pretty much cannot go anywhere, right? So it is all zeros. So if I do R star transpose, it is going to give me, so the rows becomes columns. So the first row becomes first column, second row becomes second column, third row becomes third column, and last row is all zeros becomes the. So now if I do R star intersection R star transpose, I will do a term by term multiplication, and now you see the terms which are going to retain in the matrix are the terms where we get a 1 in R star and we also get a 1 in R star transpose. Let us say, for example, this element, it is 1 here, but the corresponding element in R star is 0. So that element is going to be 0. But if I look at these 4 elements, These four elements are present as 1 in both R star and R star transpose. So, what do we see? This will give me 0 0 0 0, 0 1 1 0, 0 1 1 0 and 0 0 0 0. And these ones in this R star intersection R star transpose tells me where my cyclical net is. If we have ones kind of there in this R star intersection R star transpose, we know that there is cyclical net, and then they pretty much tells me also where is the cyclical net. In this case, again I do a labeling 1 2 3 4 1 2 3 4, and this pretty much tells me that 2 and 3 forms a cyclical net, and they pretty much forms a nice square of ones. So 2 3 in this case is going to be a order 2 cyclical net, right? So that's pretty much evident from here. Okay, let us take one more example, but before that, let me just draw the same graph in a slightly different manner, and we'll see that we don't get a nice square of ones. All I have changed here is that I have simply labeled 3 as 4 and 4 as 3. So whatever 3 is there, now that becomes 4, and let me call this some 4 prime just to say, and this becomes my 3 prime. And now the graph looks very different. It is the same graph. So we have now loop between 2 and 4 as opposed to 2 and 3, because we have numbered 3 as 4. I mean, in general, when you are, let us say, looking at a flow sheet, you don't know what the numbering is going to be like. So the same graph you can represent in different ways depending on how you number them or how you label them, right? So let us say if I put it like this and then see what do we get from here, right? So for this particular graph, which is pretty much same as that, we know that, but let me do it for this new graph which I have drawn. So my R star is now going to be again a label 1 2 3 4, and I can go from 1 to 2, I cannot come back to 1, and I can go to 4, and I can also go to 3, and from 2 I can go to pretty much 2, I can come back to 2, and I can go to 3, and I can go to 4. For 3 I cannot go anywhere, and from 4 I can go to 2, and I can go to 3, and I can of course come back to 4 because it's forming a loop between 2 and 4. And now if I do R star transpose, the rows becomes columns, and I'm going to have the first row becomes first column, the second row becomes second column, the third row is all zeros, and fourth row is like this. And now you see what is common between the two, which are all ones here, which are going to basically form the cyclical net in this case. And now we locate it at these 4 points. That is not forming a nice squares, right? We are seeing ones there. They must be forming cyclical net with something, but that is not evident from the graph because it's not forming kind of a square of ones as we had earlier, right? So what do we do in this case? We can do some kind of permutations to find loops. And how do we do the permutations? We can exchange or interchange the rows and columns. So we have already obtained this R star transpose here, and that gave me something like let me label this. So what if we interchange 3 with 4? Of course, I have seen the graph, so we can guess it. But now you can look at this matrix and see what will make the ones together. What will mix the ones together, right? So if I interchange 3 with 4, the third column becomes the fourth column and third row becomes the fourth row, right? So let me label this as some 4 prime. Let me label as some 3 prime, and this becomes 4 prime and this becomes 3 prime, right? So I can again do this new matrix with 1, 2, and now I will put 3 prime, 4 prime, and 1, 2, 3 prime, 4 prime, which is my interchange. So 3 has become 4 prime and 4 has become 3 prime. And what we should get now is something that we had earlier. And why is that? Because this column came to the left, so the 1 came to the left, but we also interchanged row, so this also went up, right? So all the ones came together and formed a nice square, right? So it may be possible that the way you have labeled the vertices of the graph, that this cyclical net is not very evident, and in that case you can interchange the rows and columns and you can see that it will eventually give you kind of a square of ones that pretty much establishes that where is the cyclical net in the graph. Okay. Few more definitions. So I can define something known as a subgraph of a graph, let's say subgraph H of graph G, as a graph which is also a graph in itself, whose vertices are a subset of the vertex set of G. I told you earlier that the graph contains a set of vertices and a set of edges, right? So from the vertex set, I take some vertices, from the edge set, I take some edges, right? And whatever graph we get as a result, that becomes the subgraph, the subset of the original graph. And they kind of represents, if you think about chemical process, the part of flow sheet, because flow sheet is represented by a graph, and I am taking only some vertices and edges from there. So basically I am looking at some part of the flow sheet, and therefore any subsystem, any sub process becomes a subgraph of the original graph. So let's take an example. So let's say this is my graph G, and I want to form subgraphs H. H can be any of what I am going to draw. So I can, for example, take only 1 and 2, and this is one subgraph. I can take only 1 and 3. This is also one subgraph, right? I can take 1 and 4, but 1 and 4 doesn't have a direct connection. In principle, in an abstract way, we can define it, but that graph is going to be meaningless. So I will not draw that subgraph. I can take, of course, 2 and 3. And 2 and 4 also I will not take because they do not have an edge in between. In principle, that also forms a subset, but it is not meaningful. And then I can do 3 to 4. And then I can also make combinations of like 3 vertices. Of course, I can in principle take only one vertex as subgraph as well, but that is also meaningless because what does it represent? So now let us look at 3 vertices. So we can take 1, 2 and 3. But I can also take 1, 2 and 4. But 1, 2 and 4 is kind of not connected together because 2 and 4 is not connected. So let's think about something else. Let me think about, let's say, 1, 3 and 4. So we have 1, 3 and then 4. That is also a 3 vertex graph. And maybe 2, 3, 4. is also a subgraph, right? So these are all subgraphs, and of course the graph itself is also its own subgraph. So these are, let's say, all the subgraphs, the meaningful subgraphs that we can get from this particular graph. So now I can define something known as a cyclical net more formally. I've already seen examples of that. A cyclical net is basically a subgraph H containing some n vertices of a graph G, which is of order n. Of course, it contains n vertices, so it becomes order n. If and only if each vertex of H is connected to every other vertex of H by a closed path. Let us say I take this entire graph, right? So 1, 2, and 3 are forming a loop. 1 and 2 are forming a loop, but 1, 3, and 4 does not form a loop, right? So 1, 3, and 4 in fact is an acyclic graph. 2, 3, and 4 is an acyclic graph, right? In fact, I could have done something like 1, 2, if I could have taken something like 3 and 4, that is also not forming basically any kind of a loop, right? So there are many subgraphs which are not forming a closed path, and only a few that is forming a closed path here. And in this case, there are basically two cyclical nets, one between 1 and 2. This is one subgraph, that is cyclical net. The other subgraph is 1, 2, and 3, because they form a closed path. In the first subgraph, I can go from 1 to 2, I can come back to 1, so it's closed path. In the second subgraph, I can go from 1 to 2, 1 to 3, right? I can come back to 1, and the same thing I can do for 2 and to 3, right? So from every vertex, I can visit every other vertex. That is the definition of the cyclical net. Now, that cyclical net can be also what is known as a maximal cyclical net, and this concept we will use quite a bit in this course. So a cyclical net H of a graph G can be said to be maximal in G if and only if every other cyclical net of G is a subgraph of H or contains no common vertices, right? So let's take this example. So we had two cyclical nets. And now I ask that is every other cyclical net is a subgraph of H. So 1 and 2 is, I cannot define maximal because the other one, 1, 2, 3 is not its subgraph. In fact, 1, 2 is a subgraph of 1, 2, 3. So this clearly cannot be maximal because every other cyclical net is not its subgraph. And in fact, it also does not meet the other condition that contains no common vertices. It could have been a maximal net if it was not sharing a common vertex. But in this case, 1, 2 is sharing a common vertex with other cyclical net 1, 2, 3. In fact, 1, 2 is a subgraph of 1, 2, 3, and therefore 1, 2 is not maximal. 1, 2, 3 is maximal because every other cyclical net in this graph, which in this case is only 1, 2, is a subgraph of this particular cyclical net, right? So this is how we define maximal cyclical net. Let's take one more example. In this case, we can see there are three cyclical nets. 1, 2 is an order 2 cyclical net. Then we of course have 1, 2, 3, and then we have 4, 5. So now we see 1, 2 is clearly not maximal because it is a subgraph of 1, 2, 3, and it is of course sharing common vertices, right? So 1, 2 is not maximal, it is out of the question. 1, 2, 3, the first subgraph 1, 2 is its subgraph, So that way it can be maximal. The second cyclical net we are forming, it is not sharing any vertex with 1, 2, 3. So either of these two conditions must be met. Either every other cyclical net is its subgraph or not sharing a common vertex. So in the case of 1, 2, 3 and 4 and 5, both of them are maximal because they are not sharing any common vertex, right? The first one is in 1, 2, 3, other one is in 4 and 5. So we have two maximal cyclical nets in this case and three cyclical nets in this case, and both the cyclical nets, right, are maximal because they are not sharing any common vertex. So with that, I conclude my discussion on the cyclical nets, and in the following class, we will see what impact it does have on the complexity of the graph and how does it influence the application of graph in the decomposition of, let's say, material balance equations on a flow sheet, and how do we actually represent a material balance on a flow sheet using the idea of graphs. So with that, I conclude here. Thank you so much.